This video we're going to look at solving logarithmic and exponential equations, and then I have a nice little formula I'm going to show you at the end of the section that's very useful in some other applications. So starting out here, we're going to show you how to deal with logarithmic equations. Now that we have our laws of logarithms in place, this should be a fairly straightforward process. One thing we got to watch for, I just put a note up here to remind myself, we have to check for extraneous roots when solving logarithmic equations. And I'll show you more about that once we actually get some solutions. All right, so if I look at my first example, this example has nothing but logarithms in it. Now the good news is there are all logarithms that are base 3. As soon as the bases are all the same, we are able to use laws of logarithms. Earlier on, we have learned that if you have two logs, same base subtracted, you could switch this left side into a single log. So log of x over 4 to base 3 equals the log of 12 to base 3. At this point, it becomes essentially a statement of equality. Think back to when we did something like this, for example. If I said 3 to the 7x equals 3 to the x plus 2, well, at this point, we would say the only possible way this statement could actually be true is because the bases are both the same, or we're taking 3 and raising it to this exponent. We're taking the same base and raising it to this exponent. Well, the only way that could possibly be true is if the two exponents are the same. Using that same train of thought, I've got some argument here that I'm going to take the log of to base 3. I've got something on the right side that I'm taking the log of to base 3. The only way this could possibly be true is if the argument on the left side was the same as the argument on the right side. So here, just based on what they call the principle of equality, the only possible way that the log of x over 4 to base 3 could equal the log of 12 to base 3 is if x over 4 was the same thing as 12. Then they would be equal. Now you just solve, and I get x is equal to 48. Now the extraneous roots, when you get your answers, this is all you got to do to worry about extraneous roots. You have to realize and remember, I'll just put a note up here, you cannot take the log of a negative. So you just have to make sure that none of your answers generate a negative argument here for your x. So cannot take logs, let's say. So can't take logs of negative values. So that's kind of the essence of it. So I look here, I say 48. 48 is going in here for x. Log of 48 would not be an issue. All good. So that's a nice easy one to start out with. Now the next one we're going to look at, you'll see a difference here. This time, the left side are both logarithms, base 10. As we know, those are called common logs. In fact, they could have left the bases out altogether. You don't even really need them. It's understood to be a 10. But the difference is it's got a number here that is not a logarithm. Last one, it was all log of something to base 3, log of something to base 3. The other side was log of something to base 3. In this situation, I would approach it a little bit differently. So I would still look here and say I've got two logs, the same base, added. I would always combine those together with my laws of logarithms and say that that is the log of x plus 2 multiplied by x minus 1. That's the product law. I'm just going to leave that equals to 1. Now our base here, I'll put it in here, but we said before we don't need to put that there, but it is understood that it's base 10. This now implies that 10 raised to this exponent is going to have to equal my argument here. So this is all the argument from here right over to here is considered your argument. So how are you doing that? Remember your notation. If I said the log of b to base x equals w, we're supposed to know how to switch that to exponential. X to that exponent would have to equal the argument. X to the W would have to equal B. So we learned that back in the beginning of our first video on introduction to logarithms. So that's basically this scenario. This whole thing here would be the B. There's your base. And there's what would be the W in our expression here. So this is going to be 10 to the first power equals the argument, x plus 2 multiplied by x minus 1. So now students say, oh, I don't understand logarithms. Well, really, let's look at this. I had to know laws of logarithms to get to here. But then, once you get it to a single log here, and either a single number or a single log here, logs have nothing to do with it at this point. Now it's just expanding this out and solving. So I've got 10. This will be x squared. Take away x plus 2x, so that's plus 1x. 2 times negative 1, that's minus 2. Let's make this equal to 0. X squared plus x, subtract 12. We're going to factor this out now. Two numbers multiply to give negative 12 and add to give 1 would be plus 4 and minus 3. That's going to have to equal 0, which gives me two possible answers. X could be negative 4 or x could be 3. And remember, at this point, you have to, not if you feel like it, you have to verify whether these answers work. So let's take this one, negative 4, put it up here for x. Right away, I've got an issue. If I had negative 4 plus 2, I'd get a negative number here. You can't let x be any number that would ever give you a negative argument. That's impossible. Therefore, this one is extraneous. Hopefully you see why. And even if it worked in this one, but not this one, it's still extraneous. It can't make either of your arguments become negative numbers. 3 plus 2 is 5. That's not an issue. 3 take away 1 is 2. That's not an issue. That one's good. So this one has an answer 3. Now, sometimes students get here and they say, oh, so if one works, the other one doesn't. Not necessarily. I've seen where they both work. I've seen where both of them are extraneous. I've seen like this one where one of the two works. You have to check every answer you come up with and see if they are extraneous. All right, on we go. Let's get another one more like that. So these are called logarithmic equations. No surprise why, because they have logarithms in them, and the unknown is part of the argument. All right, this one's very much like the last one in that I've got two logs, same base. That's a good sign because that allows us to use our laws of logarithms. Laws of logarithms says I could write that as a single log, base 2 of a product, x plus 1 multiplied by x take away 1. And it would have to equal the right side. This is just the answer over here. So we know we're going to get 3. At this point, we switch out of logarithmic notation and we switch to exponential. This base raised to this exponent has to equal this argument. Switch colors here so you can see it. So 2 to the exponent 3 would have to equal the product of these two. So now we're down to just solving a regular old, it's going to probably turn out to be quadratic. 2 cubed is 8. X times x is x squared. Subtract x plus x, those are gone. We should have known that anyway. These are conjugates. Minus 1, set that equal to 0. That'll be x squared take away 9. Factor. Nice difference of squares example, giving me two possible answers, 3 or negative 3. Do my verifying to see if these generate extraneous roots. 3 plus 1, not an issue. 4, 3 take away 1, 2, no problem. Negative 3 plus 1, that's no good. It would give me a negative argument. This one is extraneous. So then in class, we'd often have the discussions and say, oh, well, that's easy. If they're negative, you just call them extraneous. Not necessarily. Imagine that the arguments, one of them was, let's say, x plus 5. And the other one was x plus 6. Well, negative 3 would be fine. It works here, and it works here. I'm just assuming these are the arguments. Look, let's say you had log of whatever. Doesn't some base log of something. If you had a negative number, you can get arguments that are still legitimate even though you have a negative solution. So I don't want you to really think that, oh, just because you get a negative answer, it's extraneous. Often, yes, that can be the case, but not always. So we did have the right answer, which is 3. All right, so those are called logarithmic equations. What I want to now show you is exponential equations. We've already done this, but we've done them only in the situation where everything could be changed to the same base. So we did exponential equations like this. 2 to the x plus 4 equals 8 to the 3x. And then you just change this to the same base as this one, right? Like that and that. And then the world was good. So this would be 2 to the 9x. This would be 2 to the x plus 4. So then we would say this has to equal this. Well, the problem with this type of equation is that the world's not always perfect like this over here, so that the left side and right side are always able to be written as some power of a common base. Well, the nice thing is we don't care about that anymore. In fact, the method I show you here will also work over here. So even if you could change them all to the same base and you wanted to use logarithms instead, you can use logarithms. If you were to express this as a logarithmic statement, it's basically saying the log of 30 to base 3 is equal to x. You're trying to figure out 3 to what power gives you 30. Like that's it as a statement. Well, if I had a calculator that let me type that in, that'd be easy. The problem is the majority of calculators, I'd say 5 years ago, 0 calculators would do base 3. I mean, maybe some real high-end type of calculator, but now we're starting to find more and more that just your basic, under $20 calculators are letting you write in or type in logarithms to any base. So calculators are kind of advancing a little bit in that aspect. So some of you may have a calculator that'll let you type that in, you're going to get the answer very quickly. Now, having said that, that's not going to mean it's going to answer and solve all your prayers. You're still going to have to know how to do what I'm going to show you down here below. It's a neat little trick, but it works really nice. So this is, again, particularly effective when you can't change both sides to the same base. However, it would work even if you couldn't. What you're going to do is you're going to say, well, what bases can I do? Well, you can do base 10 on your calculator. That is the button that says log, common log, right? Base 10. It's the button LOG. And then there's also this one, which I briefly mentioned in our introductory video, and that's LN. It's called natural log. It really doesn't matter which one you use. I always kind of joke with students, this one you can get away with 2 letters. This one you're going to have to write 3 letters. They both would work. But every single scientific calculator will do base 10 logs and base E logs. As I said, there's a select few that will do others. Well, if I'm looking at this one, what I'm going to do is I'm just going to, again, sticking with principle of equality, we're just going to maintain equality. Maintain equality means that if you multiply the left side by 5, you got to multiply the right side by 5. If you take the square root of the left side, you'd have to take the square root of the right side. Well, if you take the log of the left side, you have to take the log of the right side. I'm going to take the log of the left side. I'm going to use base 10 just because I don't want to get in too much into natural log, save that for calculus class. I'm going to take the log of the left side equals the log of the right side. Now don't get carried away and get sloppy with your writing. This is the argument. This is the argument. So what about the base? Remember, if I don't write a base, it's a 10, which is the one on your calculator. Okay, here's the little trick now. This exponent, we're going to use the power law of logarithms. You'll recall that from our video on laws of logarithms, if I have the log of something raised to an exponent, that exponent can get moved to the front. So I can change this left side to now be x multiplied by the log of 3. Right side I'm just going to leave as log of 30. I'm going to get x by itself. I always encourage students to you could go to your calculator right now and get the value of this and the value of this. I always like to do it all at once at the end. That way your answer is more accurate because the logarithms are generally irrational in many cases. So you're going to get non-terminating, non-repeating, ugly decimals for answers. Okay, so to get x by itself, I'd have to divide both sides by the log of 3. And my answer is going to be the log of 30. So I'm going to type this in my calculator now. Log of 30 divided by the log of 3. My answer is 3.095, and we're going to stick with our rule we were using for advanced placement courses, which is where they always carry 3 decimal places. Oh, that would round off to a 6, my mistake, sorry. .096, not exactly that, so I'm going to put a dot above my equal sign to imply that it's approximately that. And that's kind of the little trick. You just take the log of both sides to a base you can deal with on your calculator. And again, in theory, I could take the log of 3 to the x to base 7 and base 7. Well, the problem is I can't do base 7 on my calculator, so that doesn't help me any. That's why you want to pick a base here that you can then use your calculator to navigate through. All right, let's have a look at this one. 6 to the 2x subtract 3, 8 to the x plus 1. 6 is not a power of 8, 8 is not a power of 6. Neither of them are both. 8 is a power of 2, but 6 isn't a power of 2. I can't change them to the same base. So what I'm going to do is take the log of both sides. The log, base 10, of 6 to the 2x minus 3 will have to equal, unless I do the same thing to the right side, it will still be equal. So students say, oh, I see, you multiplied by log. That's not what we're doing. We're taking the log, base 10, of both sides. Exponents, move to the front. 2x, subtract 3, put it in a bracket if it's multiple terms, a binomial. So it's 2x minus 3 multiplied by the log of 6 equals x plus 1, in brackets, multiply that by the log of 8. Now, log of 6 is just some number. It's like having a 2 there. Log of 8 is some other number. It's like having a 5 there. Well, a number outside a bracket, whether it's on the front or the back, distributes into the bracket. This number distributes into here. So this becomes 2x multiplied by the log of 6 minus 3 multiplied by the log of 6. Notice when I multiply these in, these numbers have no bearing on changing your argument. It stays what it is. So it's just 2x log 6 minus 3 log 6 equals log of 8 times x. So x multiplied by the log of 8, 1 times the log of 8. That's the log of 8. At this point, you're always going to be at a linear equation. So linear equations, now students look and say, oh, this is really a whole lot more complicated. No, it's not. It's just that instead of a 5, it's this. Instead of a 4, these are just numbers. What you're going to do is all the x's, collect them together on one side, 2x, log of 6, take away x, log of 8. Anything that doesn't have a variable, move it to the right. So log of 8 is going to stay where it is. I'm going to move this term, that's just some number, move it to the right side, it'll become plus 3 log of 6. Now, on the left side, I want to collect those like terms. So I want to collect the x's together. Well, they're kind of ugly numbers, so a nice easy way so that you can do this all at once in your calculator at the end is just factor that x out of every term. So take your x out front, that's going to leave you with 2 log 8. Something's wrong. Oh, that's a 6, sorry. 2 log 6. Let's fix that up here. So it's 2x log 6. This would be 2 log 6. And this would just be take away log of 8. So the x, I just, again, factored it out as a GCF. Log of 8 plus 3 log 6. I want to get x by itself. Remember, this is just a number. We're saving it for one calculation at the end. I got to do the same to the other side. 2 log 6 subtract log of 8. Now I'm going to encourage you, while you're watching the video, to pause it, listen to my instructions first, and see if you can put this into your calculator all at once. It's a skill called data entry. You got to be able to enter things into a calculator. It's a much easier process when your calculator has on-screen typing, meaning as you're hitting digits and numbers and brackets and things, you're seeing them. Some of you may still have calculators that don't have that feature. It's a little bit more tricky to do it. The one thing you got to do is you have to treat the numerator, even though there's no brackets on them. When you type this in your calculator, you're going to have to type in bracket log of 8 plus 3 log 6, close the bracket, hit your divide by, start a bracket, 2 log of 6, take away log of 8. And you're going to close your bracket. You're going to hit your equal sign. You're going to carry 3 decimals and you're going to get an answer. So again, pause the video, try it on your calculator, see if you can get the answer I'm going to get here. I'm going to pause this just for a second. I'm going to type it in myself just so I'm not wasting time. And I came up with 4.956. I rounded that off to 3 decimal places, so I'll put my dot over my equal sign. All right, and again, I encourage you to just do one computation at the very end to keep this answer as precise as we can, because the issue you can get into is you could have found the log of 6 way up here, rounded it off to 3 decimal places, rounded off the log of 8 to 3 decimal places, and then just work with the decimals. But the problem is you round off here, then you probably round off your answer again. Then all of a sudden this answer is not nearly as precise as we would like it to be. That's the advantage of keeping it like this. All right? Let's have a look at this one. Now the left side this time is a quotient. That's all good though. We're going to, like the last one, we're going to take the log. Well, this one you got 2 choices. Some of you might have noticed that, hey, these are both powers of 5. Why don't we? And this actually probably would make things easier for us. Let's multiply both sides. Now this only would help because these are the same base. We're going to take and multiply. So we're going to leave the left side alone, but we're going to multiply by that denominator. So 5 to the 2x plus 5. Whatever you do to one side, you have to do the same to the other side. That'll get rid of it here. So well, how does that help? Why does that help? Well, we're multiplying and the bases are the same. You can add the exponents. So you're going to get down to 5 to the 3x plus 4. I can't change these to the same base. Take the log of both sides. I'm going to use base 10. Take the log of the right side, base 10. Bring your exponents to the front. 4x log 2, 3x plus 4 log 5. Distribute on the right side. The left side's all good to go right now. So I'm just going to leave the left side, 4x log of 2. Remember, this is a number. Distribute it into here. 3x log 5 plus 4 log 5. Collect the x's together. 4x log 2 minus 3x log 5. Anything that doesn't have an x associated with it, we're going to leave it alone on the right side. No non-x terms on the left side, so that's all we're going to have left. Factor out the x. 4 log of 2, take away 3 log of 5, equals 4 log 5. We want to get x by itself, so we're going to divide both sides by this. So x is going to end up equaling 4 log 5 divided by 4 log of 2, take away 3 log of 5. And again, pause the video. See how you make out putting that in your calculator. So I'm going to pause it myself here for a second. All right, so I put it in my calculator and I came up with negative 3.132. I round off that third digit. Now, sometimes students are a little apprehensive. They say, oh, I got a negative answer. That's fine. You're only not allowed to have negative arguments on logarithms. Here, always go back to your original equation. The original equation, x is up in here in the exponent. There's no issue with us having negative exponents, zero exponents, fraction exponents. So we don't have to worry about extraneous roots here. That answer is fine, negative 3.132. Okay, I've got one more, I believe, here. So this one's a little bit more complicated because I have all these multiple bases, different bases. That's okay. We do it the exact same way. Now you could get into saying, oh, I could change this to a power of 2 and tidy this up a little bit. Yeah, you could, but I don't think it's going to make it much quicker. So I think I'm just going to, as it sits, take the log of the whole left side. Now this is important. What students do wrong is they think it means take the log of this, the log of this, the log of this, the log of this. That's not what it means. It means take the log of the whole left side and then take the log of the whole right side. Okay, so now the left side is a product and quotient. So you're going to use your laws of logarithms and expand this out. So it's going to be the log of 3 to the x. So these two are multiplied. So that's going to be plus the log of 2. I'm using the laws of logarithms. 2 to the x plus 1. We're dividing by this one, so that's going to be subtract. The log of 4 to the 3x. Right side will be log 5 to the 2x. So I use product law and quotient law here. Now I'm going to use the power law that says I can bring any exponent of an argument to the front and write it as a coefficient. X times log of 3. X plus 1, if it's multiple terms, always put it in brackets. Multiplied by the log of 2. Minus 3x multiplied by the log of 4 equals 2x multiplied by the log of 5. So the only thing I got to worry about is this binomial. So log of 2 has to distribute into both of these. The rest of these can all kind of stay as they are for now. X log of 2 plus just log of 2 minus 3x log of 4 equals 2x log of 5. So now it's linear. I'm going to collect all the x's together on the left side. I think now you're kind of, hopefully you're getting the hang of this. I'm going to factor out the x just so I don't have to write this all out 2 times. So as I move things, I'm also going to factor out x. So x, I'm going to have log 3 plus log of 2. Take away 3 log 4. And then this is going to come over and become minus 2 log of 5. And again, notice the x is out here. So each of those was multiplied by x, which you can see in all of those. Equals log of 2 is going over to the other side where it came from. I get negative log of 2. X will have to equal this, negative log of 2, divided by all of this stuff. Log of 3 plus log of 2 minus 3 log 4 minus 2 log 5. This will be a good test to see if you can input this stuff in your calculator properly. So I'm going to put equals with a dot over it. Just going to take a break here and get my calculator out. All right, so according to my calculator, I'm getting 0.124. There's rounded off to 3 decimal places. Okay, so what I've got here just as a quick follow-up, I got a checkup. So this is just a quick recap of what we did. Again, you might want to stop the video, have an attempt at these 2 questions, check your work, start the video, and see how you make out. So again, if you want to practice and see if you've understood what I've talked about in the last 2 sections, try these 2 examples and then start the video again and see how you made out. All right, here are my solutions. This one I notice I've got a number here that's not a logarithm base 3. So I'm going to kind of shuffle things around a little bit. I'm going to keep the log. I always like to keep the logs together. Bring that one over, minus log base 3, x take away 5. I'm going to take negative 2, move it to the right side, and make it 2. The reason I want to group these logs together because they're the same base, and when they're added and subtracted, you're allowed to use laws of logarithms. So I'm going to write this as a single log of now because it's subtraction, it's a quotient. So it'll be not like we did a couple examples earlier where it was a product, but that was because this was a plus. If it's subtract between the two logs, that means you can write it as a single log as a quotient. When you get to here, if the right side's not a logarithm base 3, you switch notations. 3 squared has to equal your argument, x plus 3 over x take away 5. And now we're just going to, I'm going to run out of room here, go up here. So that's going to be 9. I'm going to multiply both sides by x take away 5. Right, that'll get rid of that down there. So I'm going to have 9 onto x take away 5 equals x plus 3. Well, now we're getting down to something that's pretty easy for us to handle compared to what we started with. 9x take away 45 equals x plus 3. Take x away, we're going to get 8x. Add 45, we're going to get 48. Divide both sides by 8. And I get x is 6. Well, I can see the answer here is 6. So I did do it right. I should also verify, go up here. 6 take away 5. Log of 1 is fine. You just can't have 1 as a base. You can have it as an argument. You can't have negative arguments or 0. And 6 plus 3 would be fine. So that answer is all good. There's a logarithmic equation. There's an exponential equation. These are the ones that we just finished before I started these checkup. Oops. Okay, so this one, that's the one we just did. Pretty sure. Yeah, it is. Obviously not going to do the same one again. So that's a good example anyway. As long as if you can follow that, you'll be fine. Good news on the good news, that is the answer we got. So that's a good sign. Okay, last thing I want to show you is a neat little formula. It's called the change of base formula. I think I have it highlighted down below here. Yeah, see down there in red. And it's just showing you that if you had this and you had, so the log of n to base b equals x, or you had b to the x equals n, and I said solve this. Well, right now you would say take the log of both sides. You'd bring your x to the front. And then you'd solve for x, which would be the log of n divided by the log of b. Well, in theory, I chose base 10 because I was going to do it on my calculator. But in theory, there would have been nothing stopping me from choosing base 7 here, as long as I used base 7 over here. I could have used base 17. I could have used base 17. I can pick the base, which means that this down here could have been the log to any base as long as this one down here is the same. Now look, notice where this was. So the n was your old argument and the b was your old base. So what we say is, in words, it's the log of the old argument divided by the log of the old base to whatever new base you want to switch it to. And that's why they call it the change of base formula. So I've got it down here. That's just kind of a derivation or a proof showing you where it is. So this would be, supposing I was in base B, but I wanted to change to base A. And again, these B and A are just representative of any numbers you would want. So I could be in base 7 and want to be in base 4. So if I add the log of n to base B, it's the log of the old argument to whatever new base you choose, divided by the log of the old base to whatever new base you should choose. So if I look at these two examples down here, let's think logarithms before we actually figure this out. This is saying 5 raised to what power would give me 45? Well, I know the answer is somewhere between 2 and 3 because 5 squared is 25 and 5 cubed is 125. So it's probably closer to 2 than it is to 3. With this formula I showed you up there, if you have a calculator that lets you type this in, you really don't need to know this formula. If you don't have a calculator that lets you put in any base, this is a great formula to know, because now I can do this on my base 10 calculator. All I do is switch everything to base 10. So what do you mean switch to base 10? I use the formula. The formula says take the log of the old argument to whatever new base. So I'm going to go 10, so I'm just going to leave it out. And then I'm going to take the log of my old base to whatever base I pick up here. Now you take your calculator and you can just type that in your calculator. Log 45 divided by the log of 5. And I get 2.365, which, based on what I said to start with, that sounds quite reasonable, because we said it had to be somewhere between 2 and 3, probably closer to 2 than it was to 3. Okay, this one over here, I'm trying to figure out 3 raised to what power gives me 7. But I want it to be exact. I don't want to just guess and test and play Price is Right guessing game. I want to be able to figure that out on my calculator. Now, just to show you the other, pause this for a second. Sorry about that, distracted by a phone call. So as I was saying, this, just to show you, I'm going to pick base E. You say, oh, what's base E? Remember, don't worry about it. You'll learn more about it in calculus, but there is a button on your calculator, the LN button. It's usually right next to or above or below the, it's usually a capital L too, I think. It'll look like that. I'm going to go ln of 7 divided by ln of 3. This is the way we would say it would be the natural log of 7 divided by the natural log of 3. Well, student B says, oh, I didn't know I could use that button, and they do it this way. The log of 7 divided by the log of 3. Just to show you, you can try both. You're going to get the same answer. It doesn't matter what base you choose to put these to. They have to give you the same answer because they're both being used to evaluate the same thing. 3 raised to what power gives me 7. So if I use the natural log button instead of the common log button, natural log of 7 divided by the natural log of 3 is 1.771. And if I do the common log root instead, common log of 7 divided by the common log of 3, of course, as I said, what happened? I get the same thing. So as I said earlier, natural log, ln, this button here, and log are the two buttons that are on every single scientific calculator. And as technology has progressed and got cheaper and cheaper to make calculators do neat and fancy things, you can now find calculators that will actually do this for you, and they let you type in any base you want, which is a nice advantage because then you don't need to do this extra work like I had to do here. All right, so that's a neat formula called the change of base formula. That finishes our unit on exponential functions and logarithms. I have a few practice questions that you can look at. And again, when I put these up here, it doesn't mean you have to do them all. I just suggest a sampling of these. Check the answers in the back. Once you feel confident with those, there will be a short assignment to finish up our logarithms component of our pre-calc 12A course. All right, reach out if you have any questions, and best of luck.